to the other pathways we've learned. So for example, connecting maybe fatty acid synthesis to photosynthesis is probably a stretch. So if he asks you a pathway question for photosynthesis, it'll most likely just involve photosynthesis. But usually the ones that involve mammalian pathways are kind of connected. So let's look at it more in depth. So I put in here the name of the compounds. I don't care about writing them, and you shouldn't really worry too much about writing them besides the ones that he wrote in the lecture. But what we're going to focus today is the number of carbons. So we're going to go over the cycle and number the carbons essentially, so that we understand why this works. So we start off with our CO2, which is 1 carbon. And so the way I'm going to notate that is 3 times 1, because we have 3 molecules of 1 carbon CO2. Now, we also started with ribulose bisphosphate that we said earlier. And so we're going to start off with 3 molecules of that. And so to start at point A, scenario 1, we have 3 molecules of a 5 carbon backbone, and that interacts with 3 molecules of a 1 carbon. And so hopefully you guys can do the math. When they each combine, then initially what you'll make is 3 molecules of a 6 carbon molecule. And then what happens after is that splits into 2. Each 6 carbon molecule splits into 2. And so the final result then is that you get 6 molecules of a 3 carbon. And so if you can follow along the lines, you see the diagram kind of explains it in this way. You have 3 molecules represented by 3 lines. And by the time you get here, you're at 6 lines, which means you have 6 of 3-phosphoglycerate. The reason why is because when the 2 of them combine to form 6 carbon molecules, they split into 2. So hopefully this math makes sense. But the total number of carbons still stays the same. At this first step, the total number of carbons is 18. At this step, it's still 18. And then at this step, it's still 18 carbons. So then we charge that with ATP to form 1,3-bisphosphoglycerate. And then we reduce it using NADPH, and then we get GAP. And so overall, you should think I didn't change any of my carbons in this step. And so in this scenario, all we did is charge it with energy and electrons. So now you're left with 6 molecules of GAP, which is 3 carbons each. So how do we make the sugar now? So our 2 goals is to recover the starting molecules and also to make sugar. And so the way it works then is we're going to take 2 of these, 1 as a GAP and 1 we're going to turn into DHAP. And we're going to use these 2 to form a 6 carbon molecule over here, which just becomes another 6 carbon molecule there. We're going to take a 3 carbon molecule from that same pile, put it here, and put it here. So essentially, if I were to highlight what had happened, this group of gaps that we just produced here are now located in all of this. And so to kind of clarify what the hell just happened, essentially, this 1 DHAP we produced will be used to form a sugar. So you can see this is the only part of the pathway that leaves, which makes sense. It's the only part of the pathway that will be sent out to form a sugar. Surprisingly, out of these 6 gaps, only 1 will be used to make a sugar. The rest of the 5 are going to be used to form your backbone. And so through a process we're going to talk about in the next unit, as we talk about the pentose phosphate pathway as well, we're going to essentially turn these 5 into ribulose 5-bisphosphate. And so to do the math, so hopefully this makes sense. At the gap stage, we had 6 molecules, each 3 carbons long. And then we said that at some point in time, we're going to get rid of 1 of them. So 1 disappears to be a DHAP. And then the rest are used up to reform the ribulose. And so this should be 3 carbons long. And now we have 5 molecules. Oops, 5 molecules. I'm just going to put mole, 5 mole of 3 carbons, which hopefully you guys think of it as 15 carbons. And then to kind of conclude this collection of 5 will then be used up to reform the ribulose 5-phosphate. And ribulose 5-phosphate will have 3 molecules of that, and each molecule is 5 carbons. So we retain the 15 number of carbons. And so if you got lost from all these calculations, what I'm just basically trying to say is it doesn't make sense to read this pathway as a one-to-one. If you look at the pathway we just showed earlier here, if you look at it 1 molecule at a time, it doesn't make sense. The math doesn't make sense. How do we form sugar and how do we recover the initial 5 carbon molecule when we only have 1 CO2? It doesn't. In order for this pathway to net produce a sugar, it kind of has to happen in this ratio. So essentially, the only way for us to produce 3 carbons of a sugar intermediate is to have 3 cycles occur. So basically, a ribulose 5-bisphosphate, 3 of them will have to interact with 3 CO2s just to produce 1 3-carbon molecule and the rest to recover. For the sake of this class, what do you need to know from this pathway? It would be best for you to understand the counting. Hopefully, when you draw this pathway on your cheat sheet, that you can label the number of carbons to keep in track of where they are. If you just write this down, it'll help you recognize what step of the pathway. You guys already know probably what's going on in these steps. It's getting phosphorylated, it's getting reduced, so it should be okay. But overall, I just wanted to go over this slide so that you understand how do we actually produce a sugar when CO2 enters the pathway. So now let's talk about this middle part right here, which is where people get really confused because the diagrams look really hard. Let me put in here a couple slides real quick. So these are the slides I have for the reactions that we didn't talk about, the ones that are located here, where we use ATP and NADPH. So I put in here the enzyme names and the reaction, but you can notice that the reactions you've seen so far are pretty much the same. So in this case, the first reaction, the 5-carbon molecule reacts with the CO2 to form a 6-carbon molecule, which then splits into 2. So then that becomes 3PG. But the rest of the reactions are really much the same. It's just phosphorylation and then reduction. So hopefully you notice that you go from a carboxylic acid group to an aldehyde group. So that is a reduction. And so it makes sense that in the process, we've used NADPH. So all of these pathways are about the same as you've seen before. So I'm not going to spend time on these ones because you've seen it before, but I'm going to go over the carbon shifting ones afterwards. So please refer to these slides for those reaction mechanisms. So in every year, he asks questions about transketolase and transaldolase. So I want to go over this because this is always the first question, always in his exams. So there's 2 enzymes we're going to talk about, and that's transketolase and transaldolase. So what does that look like? So I have here 2 random sugars, and you'll see that they're not so random. And in this scenario, we have transketolase. So what is transketolase? So essentially, it transfers carbons from one sugar to another. So if we look at this example here, we have erythrose 4-phosphate and cellulose 5-phosphate. What we're going to try to do is that erythrose 4-phosphate is 4 carbons, cellulose 5-phosphate is 1, 2, 3, 4, 5 carbons. What we're going to try to do is transfer carbons from one molecule to another such that this becomes a 6-carbon molecule and this becomes a 3-carbon molecule. So that's the net effect of this reaction. It's basically take 2 carbons from this and move it to the next one. And so this is often drawn by Professor van der Heyden as such. So let me try to draw how he normally notates this. So he normally writes down the reactants on the left. Oops. And then he writes the products on the right. And then afterwards, he would draw this. So what this means is, and then he write down TK. So this is a notation that we normally use to draw transketolase reactions. But what's going on here, you should imagine, is when I look at this, I like to see transketolase, what is being transferred. So for transketolase, 2 carbons are being transferred. So the way you should read this is, this 4 became a 6 and this 5 became a 3. So then I know that 2 carbons from this 5C was moved to the 4C. And as a result, you produce a 6C and a 3C. So that's how we conceptualize transketolase. And so here in this drawing I'm showing you right now, let me show you exactly what got moved. So generally, when you have a transketolase, you have a aldose sugar and a ketose sugar involved. So all transketolase reactions, the 2-carbon comes from the ketose and is given to the aldose in all of these scenarios. And so if I give you these 2 sugars and ask you, do a transketolase reaction, the first thing you should do is, I guess I can write down here, step 1 is to figure out which is the aldose and which is the ketose. So that's the first thing you should do. And then secondly, now that you've identified what is the aldose and the ketose, you pick out the top 2 carbons of the ketose. So in this case, it will be the highest numbered carbons. So in this case, carbon number 1 and carbon number 2. So I'm going to pick those out. And essentially what I'm going to do is take that and move it to the aldose and turn this last alcohol now into a carbonyl. And so as a result, this becomes the remaining product over here. And then this 2 carbons gets copy pasted to the aldose. But there's specific points you need to remember. One is that when you draw the sugar of the newly added sugar, the OH goes to the left. So whenever you draw this, you should not, you should be particularly pay attention to the carbon of the former carbonyl. When you do a transketolase reaction and you will now turn this carbonyl into an alcohol once again, you need to remember that if you're doing a TK reaction, to point it to the left. It is very critical because on the exam, we actually check that particular one. And if it's transketolase, we expect you to draw it correctly. I put in here a mnemonic in case you want to remember. The transketolase transfers 2 carbons and it points to the left. The opposite reaction is what's called transaldolase. On the other hand, this is the mechanism of transketolase. Essentially, we use TPP. Do you need to memorize this pathway by heart? No, but I would recommend to write it in your cheat sheet. And if they ever ask you to write like a synthesis style question where they ask you how might this reaction happen, all you need to do is when you draw this mechanism is to draw the 2 arrows that we have been accustomed to, right? TK at the top, and then cofactor is TPP. If you have this set up complete, you guys should get full credit. So hopefully you guys can look into this, into the mechanism. So when you solve it, as I said earlier, you want to identify the aldose and the ketose first. Identify the 2 carbons that needs to be transferred, transfer it and make an OH to the left, and then turn the former OH that was right here into a carbonyl. So refer to this page if you want to remember how to solve those problems. The other problem is the transaldolase problem. And so when you use a transaldolase, it's the same mechanism with a little twist. For transaldolase, instead of 2 carbons, it's 3 carbons that are being transferred. And then when you form an OH, you form it on the right. And so when we look at this reaction again, we have an aldose on the left and ketose on the right. So the first thing you want to do is figure out where is my ketose. So in this case, the ketose is this 7 carbon molecule, whereas the aldose is this 3 carbon molecule. So what we're going to do is, because we know it's transaldolase, we're going to spot the top 3 carbons first. After knowing that it's these 3, we're going to move it to our aldose. We're going to turn this carbonyl into an OH, but because we know it's transaldolase, we're going to draw that OH to the right. And then we're going to turn this OH over here into a carbonyl. And so as a result, from a 3C, 7C, we get a 6C and a 4C. So how I would draw this in a shorthand version is TA, and then 3C, 7C, 6C, 4C. So hopefully you should remember aldolase transfers 3 carbons, but it does the same thing. It basically transfers carbons between one sugar to another. You can think of aldehyde having 3 syllables, and so you can remember transaldolase as something that transfers 3 carbons. So similarly, to kind of go over it like transketolase, the mechanism is located here. It uses a lysine residue, and they often call it a Schiff base. So if they ask you what the reagent is for a transaldolase mechanism, what we accept as answers is you can write down Schiff base, you can say Schiff base, or you can write down RNH2. That usually will suffice. The exact arrow pushing is located here. I trust that you guys will be able to read these arrow pushings, but essentially, this is the particular reagent that we need, or cofactor that we need. So please remember your cofactors, because when they ask you a pathway question, that is the more important part than memorizing the arrow pushing. So to solve TA problems, again, identify the ketose, identify the 3 carbons, move it. Remember, OH goes to the right, and then you have the leftover in there. And I will say the first question in every first section in his exams always is almost a set of 6 problems where he has a collection of sugars on the left and then an enzyme in the middle. It could be transketolase or transaldolase, and then he'll expect you to be able to draw the product. So make sure you want to be able to solve this problem, but also feel free, you need to be able to analyze it. If he gives you the reactants and the products, you need to be able, and he blanks the enzyme so that you don't know what the enzyme is. You need to be able to kind of identify how many carbons got transferred that would produce this question. So keep that in mind. So after that brief digression, let's talk about where that applies into a lot of things now. So here's an example of how this problem can get really complicated. So in our scenario, we start with a 4 carbon molecule, which I'm not going to name, and a 5 carbon molecule. And you can actually take these 2 and end up with a 6 carbon and a 3 carbon. So the way to do that is to create a succession of transketolases and transaldolase reactions. So here I have a transketolase first, which hopefully you guys remember is a 2 carbon shift. So in this case, we're taking 2 from this 4 carbon. So now it becomes 2C, and we're giving it to 5C, so it becomes 7C. So 2 carbon shift. And hopefully you guys remember, this is a TPP kneading mechanism. And then transaldolase transfers 3. So then the 3 comes from the 7. So that's why the 2 becomes a 5. And then if we get rid of 3 from here, we get a 4.